It's our pleasure to have Clément Canonne as our invited speaker. Clément is a computer scientist with University of Sydney. His research expertise is in learning theory and distribution testing. Today, he's going to talk about Minimax bombs, measuring and testing under the restricted measurement.
Thank you. I want to start by thanking the organizers and all of you for being here. I know it's the first step of the morning. Also, if at any point I say something that sounds fishy or weird, or like, please ask. Chances are, if I say something like that, you're not the only one wondering what's going on. Also, I know I have so access, so I can also not help the communication. So I'm going to talk about Minimax bound for estimation and testing under restricted measurements. Hopefully, that's going to make sense at some point in the talk. In like the usual computer science talk fashion, I'm going to start by going very slowly on things you all know, and then I'm going to accelerate just when it gets interesting, and hopefully I won't have time to actually cover that. So if at some point I see someone putting the slip out there, go faster. This is the plan of the talk. So first of all, try to explain what I'm doing by learning and testing and what the talk is about. A little bit of the centralized setting, what I call the centralized setting, which is no restricted measurements. And then like going beyond and like meeting you with like all the new variants of the settings I'm considering. And then taking communication and privacy constraints as guiding examples. And at the end, well, given like the audience, I'll try to look that back to something quantum, or at least like I think there are connections. Hopefully they are real. And then like at that point, I'm gonna get back to you saying like, if you have any idea how to solve those things, please contact me. So I'm going to use some little icons. They're going to be exaggerated. So the dice are when I use randomization, specifically randomness. So there's going to be like private randomness, shared randomness. There's going to be some interaction, distributed, the distributed setting in there, and like privacy is the Again, I'm going to go back to that, feel free to ask. Oh, and that's the best I can find. Last thing, I have to apologize. A lot of that is my own writing. I grew up convinced I knew how to write well, and I've been told actually it's not that good. So what I'm learning and testing. So if you've taken this statistics 101 at some point, like this is NIID samples from some like unknown thing. That's going to be a very key solution. I'm going to call that V. I'm going to make a bunch of abuses of notations because most of the things are discrete, but you can make all of that for only the homogeneous setting, the right keywords. And your goal is to estimate something about that unknown probability solution. And that's something that could be like, oh, I actually want to learn the whole thing. So I want to learn the solution, so I have to be at such that the expected loss is small. So I want some loss function, like the expected, like the randomness of the n samples, n samples, and I've got the target error rate. Okay, that slide, I think I don't need to explain what those things are, just so that we're all will be on like the variable rotation using KL divergence, L2 square, K square divergence, and total variation distance. I'm going to use those there, and I'm going to focus in particular on the total variation distance. There are various reasons for that, but I'm happy to elaborate on this. But this is going to be the kind of the distance measure I'm focusing on for the rest of the talk. So in the learning settings, I want to do density estimation. But I could also want to do estimation. I want to learn some parameter, some functional theta of P. So if P is from the parametric to family, for example, I want to learn the parameter. But it could be I want to actually learn, I don't know, the entropy of what is the entropy of the distribution. I want to learn the support size, that kind of stuff. So I mean, this is basically like almost the same thing. I just generated it by putting theta somewhere. I could learn putting a mean because that's going to be something like that. I could also want to do some testing, and I guess we're all kind of aware of it. This English, I'm using a very specific variant of it. So I want to learn something about it. I want to know whether I do this correct or not. So I'm going to do this. Here I'm going to focus on goodness of fit. So is P equal to that model Q I defined? Or it's a composite problem. Is it like far from it? Is it statistically far from my evidence? So the alternative is basically everything outside the ball, TD sample of previous exam. And my goal is to output decisions such that I won't mess up too much. So the type 1 plus type 2 errors are bounded by some small constant. At this point, I think a lot of people will hate me because that's more constant. I don't care about it that much. So that's related to the error experiment, but I think of it as like, this is not what I care about. So I guess that's kind of the decision. I think of that as arbitrary. So I'm putting 110. Sometimes people use 1/3. The goal is really the way I see it, I'm focusing on kind of sample complexity. So as long as I achieve small error, that's good enough for me. I can get arbitrary small probability of error by just repeating and taking a majority vote. This is only good up to constants, and even not necessarily that much. But that's my baseline. So yeah, I'm really much focusing on the finite sample case and not caring too much about the actual error probability. My goal is to get the sample complexity right up to constants. Is there any question at this point? You still don't very good. So, also it's not just the writing, my drawing skills, but one of the things I'm going to focus on is discrete distributions. So I've got a discrete distribution of the elements, and since I know the domain, I'm just going to assume it's the integers for one. And I want to learn that thing under iterations. So I want to test if it's uniform on the elements. Those are the two main tasks I'm considering here. So you might notice that in 2 slides I already lost a lot of generality because I was like, I want to test whether P is equal to Q and I know Q, and now I it's due to the uniform distribution of the domain, which seems to be like a pretty strong restriction. Actually, it's without loss of generality. There's like a nice prediction that says if you can test against the uniform distribution, you can test against any fixed distribution you already know. And what you're going to lose is a factor like 9 or 10 in the sample complexity, so the number of samples you need, which some people care about, but I don't, so it's all good fun. So I want to either learn that general distribution P up to total variation distance psi, or I want to test whether it's uniform or epsilon far from uniform total variation distance. The second one is continuous eigenfunctional versions. So again, I'm very happy to make simplified assumptions. I'm just going to assume it's spherical. Another way to look at it is like there is a vector plus y naught. I want to learn the vector, the mean vector. And eigenfunction, like think of D as the very large. So I want to learn the mean and L square loss. So I want to output a vector mu hat, which is close to mu in an norm. Or I want to test whether the mean is 0. There is no signal, it's just like nothing plus y naught. Or if the mean is has large magnitude in the distance, so there is a signal plus y naught. And instead of focusing on T distance, and right now just L2. The reason is for spherical versions, L2 distance between means is basically proportional to total variation distance, as long as that epsilon is small. Of course, if the distance between the means becomes much larger than 1, then that fails. But in the close to 0 regime, there is a direct response. So those are the two suspects, like the eigenexamples on that. So the discrete distributions of the elements or eigenfunctional versions in the dimension. And in both cases, I want to either learn or test whether they're like the reference or far from the reference. And okay, before going to like, oh, what if we have restricted measurements, etc., what can we do if we actually get n IID samples? So I mentioned the sample complexity. It's really, I have n samples drawn from that unknown distribution that are free accessible again. Even, let's say I don't care about the computation, I mean, I would like that to be computable and efficient, but even if I don't care, how large must n be to be able to solve that learning or testing function? As a function of all the parameters you want to put in there, but like let's say G and etc. There are some refinements that will be like, oh, that's going to depend implicitly on some function of P, the thing that I don't know, that's not there. So dimension and desired accuracy, what is the smallest n I need to be able to solve that. And so the minimax complexity of all possible solutions. So at this point, I'm coming to you, and here's a quiz. If I think of D very large, it's n very small. So I had a lively discussion about asymptotics and abuse of theta and big notation yesterday. So this is exactly that. You have two parameters, one of them goes to infinity, the other goes to 0. I want to learn an arbitrary distribution P over D elements to perturbation distance epsilon. How many samples will it expected to be us? Yeah. I need something that grows with the domain size, linearity. And even worse than that, I guess you can guess the dependence on epsilon, because if even if D is equal to 2, just to learn the bias of the code, like then we 1/2 versus then we 1/2 plus epsilon, I will need 1 over epsilon squared, something that grows like 1 over epsilon squared. So there are two ways to put those things together. It's like so I need D over epsilon square samples of the universal constants. I think the constant is actually something like between 1 and 2, but it's aggregating to solve this problem. Which is kind of bad news because that's linear in the database. Now, if I want to test whether that unknown distribution P is the uniform distribution, U is the uniform distribution, or is a distance at least epsilon from it, what is the sample complexity? And just so we're clear, it's at most D over epsilon squared. Right? Because if I can learn the thing, I can learn it and then check whether it's close to the uniform amount.
Question before you ask that question, do we have a guarantee it's either the one or the other?
Oh yeah, for this, yes.
That's a huge difference, right? If you don't know whether it's close to this epsilon.
Yeah, so this is a promise problem. Or you could think of it as that if it's not, then like you are the ones out of it. So any guess? So it's at most 0 epsilon squared. So I'm not very much second. The tight thing is square root. And there are several ways of thinking about it, but not quite accurately, but kind of think of that as the birthday paradox. You want to test whether something is uniform or not, until you, like, at some point, 2 of your samples take the same value, you have 0 information. You can't distinguish even whether it's like uniform or like half of the domain. Literally, you've seen every single thing once. Then make that conformal, and you get so the good news is square root of the domain size, which is big smaller. The dependence of epsilon is mentioned in that. Now that given the title of the workshop, maybe it's worth going beyond IID. So I mean that was all good but like, that requires me to have the n samples in my hands. I mean the algorithms are not that complicated, a lot of them are like, actually just linear time or near linear time in the number of samples, blah 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 blah. That does require me to have all of that nicely installed. That's not necessarily the case if the data is distributed, for example. You know, we all have a cell phone. Think of that data as like, you know, you're going to send something to a centralized server. You might not want to have to send log D bits of information every day or something. You also might have some information on computational constraints on various cases. So, for example, maybe you have a memory limited device. You can't actually store those n samples, which is n log D bits, in memory. Again, D is large, n is large. That's not very well. So that's some applications like screen setting or whatever. Just think of that as like, how do I do that if I can only store very little in memory? You also have the privacy constraint, which is just like, or maybe that data is sensitive. Maybe I mean, either I'm not allowed to store it, so that goes back kind of like to the level constraint, or actually the users do not want you to have access to it like this. You know, if I'm trying to test something highly sensitive, like is like the use of drugs uniform like among the population, maybe people don't really want me to know like what drugs they're using. So then you have that kind of like the information constraint is you don't have access to the actors. And you also have limited types of measurements. We're going to get back to that again. That could mean many things. That could go from game theory kind of thing, like, oh, the kind of access you have, like, you have an item, you set the price, and like, well, what you get is like people buy it out. So you get one bit of information, which is like, what's the price of that? What's the valuation people give on that item above the threshold I set on it. You can set that actively, but you only get one bit of information on the very fast graph. So you have all those things, and this is beyond IID. Hopefully, I can convince you of that because that's a measurement I make. So maybe what I'm going to do for one sample is not the same as the other. So you have some extra things on you. So there are many limitations in that setting, but the thing we're going to consider is that we have n users. And just to keep that correspondence, each user has one sample from the unknown distribution. So same distribution for everybody, but each of them gets one sample independent of the others. Only one. And then there's a center, so like a server or whatever, that has nothing, but is the one that is going to run the computation, it's going to run the test. And each user can only send one limited type of message. So either they can only do a limited type of measurement, or they can only send a limited type of thing. And so the goal is you want to perform the same task at the server. So hopefully it's clear to everybody that the sample complexity is going to be worse. You add a restriction. And I'm going to call that a local constraint because the constraint applies to each person independently. This is my code. So you have the same distribution P dot. Each of the end users gets one sample from observation. They pass that to some channel. And each of them gets a message, they send that to the server, the center that runs the computation. And those channels to model the constraint have to come from like some particular family. So like, particular form. Again, if there's any question beyond like where did you learn how to go, I'm happy to answer. So here's, okay, so since there's a very strong information theory flavor here, I guess you're going to APA remember like this is our model of the channel. I just said like, it's a randomized function. But yeah, so that's not necessarily the best notation, but yeah, the channel function is just literally a randomized function that maps a sample to a message. And I'm going to use that notation, the value of y and x, so it's the probability that only given the sample x, I get that message. And I'm going to give a set of allowed channels. That's the only thing the users can use. So just some examples. What happens if that family includes the identity mapping? Then I get back to centralized system. The best thing to do is literally to just send your sample. You don't have more information to send. So any interesting case, you have to make sure that it doesn't include the identity mapping, because otherwise we solve that already. Okay, now I'm gonna need like the various flavors of thing that I consider. So what I call private kernel has nothing to do with privacy, which is going to be very confusing because I'm going to talk about privacy later. Private kernel that puts in the communication complexity interaction. It's just those things are independently randomized. So each user has their own personal source of randomness, but that's their own. Nobody else sees it. So that's one. Then you could say, like, what if it's jointly randomized? There's like a magic random seed that everybody has, or like they observe like blotches on the sun or whatever. And they can use that to actually randomize geometry data. I want to say that they also have their private source of elements. I still assume that they have their own like time that they can test. That's actually necessary for some application. But they also have on top of that access to that dependency. Another way to look at it is that the server starts by sending all everybody one like large random seed, and then they can use it that way. It doesn't depend on everything. And the last one, more annoying to analyze, is fully interactive. I'm just saying sequentially interactive, which is already pragmatic. So the first user sends their message, and then everybody else sends it. So the second user can actually, like the message can depend on the first, etc., etc. So there is some array of users. And, I also assume there is public randomness because, unless you have a communication constraint, the first message could just be like, you could have a bunch of first users that just each of them send a random bit, everybody observes it, and then you use that for the public randomness. And then you have a fully interactive thing that's sometimes called the black box message, like the protocol is defined as like the first user writes something that everybody sees, and then on that someone else talks, and they can take turns. And so most of what I'm about to talk about applies also to that, but it's just very messy. Yeah, it's the main problem to formalize or fully deploy. So just some things. Why do we consider that? In terms of implementation, deployment, or it is to actually have one of those protocols, private coins are max. Like, it's the simplest setting you can deploy. Public coin, a bit more annoying, you have to have that downstream seed sent to everybody, or at least you need to find a way for people to coordinate on a public coin. And interactive is the worst. Like, that introduces latency. People have to wait for the previous message to arrive, and you have that whole kind of nice dependency in the way you implement things. But in terms of sample complexity, it goes the other way, right? Because you go from more restricted to less restricted. So it's kind of important to understand the trade-offs. The best case is proving that this for a task that what you can do something, the sample complexity, the private key setting is not worse than in the interactive setting. Because then if you can prove that, you put an upper bound in the private key setting and it matches the lower bound in the interactive setting, then as an algorithm designer, you don't have to worry about anything. You can just be like, I'm going to use this, it's simple to implement, it's optimal to constant factors, and I'm done. So that's the goal, and unfortunately, that's not always the case. Is that kind of clear? So I said I would use those two examples as learning examples. So communication. You could consider more complicated things like each user has a different constraint, but let's just say each user can only send L bits. And again, just for the task I talked about, what is the restriction on L? So at this point, what's the natural restriction on L? L is at most log D, log-based log D. Because otherwise, again, there's nothing, there's no constraint. You can just send the whole sum. Like you can put a number between 1 and D, and put that. So think of L as small. And implicitly, I'm gonna local privacy. So think that side I managed to pretty much have everybody unhappy with my notation. So I'm gonna use rho for privacy, right?
One question: how do you define sample complexity in the setting? Before you had N for the number of samples, now you have for the users. How do you repeat the thing?
So that's why each user has one sample, right? So the sample complexity is just the number of users. That's convenient. If you want to go for more complicated things like N users, each of them can have N samples, and sample complexity will be N and times N. Then you also have some trade-offs that are big. So I don't know how many people are familiar with differential privacy. Okay, so usually epsilon is used for the privacy parameter, but I already used epsilon, so I'm using rho. That tends to hurt a lot of people, and I'm missing also rho is for most people here means something else, so I'm sorry. When I use row, it looks like a P, so privacy, and row is P. But the differential privacy constraint basically says that like, I have an algorithm, the output of the algorithm should not reveal too much about any particular data point that was given in the input. So in particular, it's randomized, so the distribution, the probability that the outcome is in any particular outcome should vary by, like, let's say at most 1 plus or minus row factor. No, that's the goal. 1 plus or minus row is kind of annoying, and for other reasons, nice interpretations. We use e to the row, which for small row is basically the same thing as a much nicer and for other, in this case, we're looking at local privacy, so the privacy constraint is at each user. So each user is going to output something, but the message they output should not, basically every message should have roughly the same probability, regardless of the input. So think of that way. If I observe, if my sample is X, maybe I'm going to output like some Y with 20.5. Or if instead of X I had something else, like a different sample, I should still output Y with roughly the same probability. Roughly, because I mean, if it's exactly the same probability, then I'm giving 0 information. And but it should be within some like 1 plus or minus row factor. So that's why we use this. Think of row as small. In practice, though, people use row up to 10, and I think that application starts failing quite badly. But yeah, think of to the row as 1 plus row. So again, that's kind of a weird concept because you want to perform a task that you want to analyze the data without knowing too much about the data. So again, think of when row is 0, then like you're in trouble. There's nothing you can say. When row grows to infinity, you have no privacy, and in between, like you quantify roughly like how much you can reveal about any partial person data. Any questions?
Why is it just a one-sided question?
Oh, well, it's one-sided because it's for all X and X. Right?
Oh, that's
And yeah, also, if you're familiar with different privacy, there is a notion of approximate local privacy, like on top of the multiplicative factor and an additive delta. But first, it's messier, and second, for testing and for local privacy, basically you can trade delta for rows. So it's one way. So again, the two concepts are like one of them I can't send too much, and the others I can't reveal too much. So now we want to do the same thing, but in this new setting where you don't actually get to see the data. So again, here is the same quiz. I want to learn an arbitrary distribution P over D elements to correlation loss exam, and I got an L-bit communication constraint. What is the sample complexity? So again, just so that we're clear, it's at most D or it's at least D over epsilon squared. It's a strictly outer product. And again, another thing, whenever I say that when L is log D, I should get back D over epsilon squared. Then I can have my constraint disappear. So hopefully I get something kind of smooth in between. And here's what it looks like. So it's worse, and it's worse by a factor D over 2 to the N, which again, it's kind of good because when L is log D, then this is the best possible. Right now, it's bigger because this is just the upper bound, and the second part, I'll claim it's optimal. And under different privacy, local privacy constraints, same thing, you have like a D over rho, like D over rho square extra factor, which is a bit weirder to interpret. It's kind of annoying, but this is just because I said that rho is close to 0. Actually, that rho square is not rho square; it's e to the rho minus 1 squared, which is where it goes to right. If you take rho going to growing, you can see that it actually you have a smooth layer as well. And from this, you can also think of that as you pay an extra d over whatever constraint you have in the sample complexity. So d over 2 to the L extra multiplicative factor, or d over rho squared. So that's the price of the constraint. And one nice thing is like this is attained by private kernel protocol. So you don't need share randomness. You can just, yeah, this is kind of nice. The other ones are actually pretty simple. And that just works then. So, okay, now what about testing? So that was for learning, and we went from d to d squared. So you think of like everything else being constant. So what about testing? We have square root d. What do you think it's going to be now? So, all of those actually make sense. So, same thing, except that now it becomes weirder. So there's still a multiplicative factor, so instead of square root d, I get d to the 3 outside 2 to the L. Well, I think it's not that weird, right? D over 2 to the L times whatever I had before. So I get the same multiplicative factor that I had today. And same for price. What becomes weirder though is you can do better if you're vector autonomous, like a lot better. And one way to look at it is here the multiplicative factor was d over 2 to the L, but here some square root d over 2 to the L. So somehow I think shared randomness allows you to perform testing much more efficiently. And same thing for privacy. Actually, I'm putting those two, but I mean, they look very similar. The experiments are the same. It's kind of, you can really think of privacy and communication constraints as like similar in spirit, and in particular when the privacy constraint becomes kind of weaker and rho is greater than 1. There is some correspondence between the two. You can think of privacy as some kind of communication constraints there. So it's not necessarily that good. But going back to the question,
Just a question about that is d over rho squared or d over rho? Is it just a square or is it?
d over rho squared.
Yeah. Okay, so it's great.
Oh, it is great. Yeah, this one I'm not actually quite sure why. Like why this part doesn't get the square root. Yeah, so interactivity doesn't matter. So I'm going to give some lower bounds there. But yeah, it's for learning, it was just like what you can do with private randomness, you can do better with public randomness or interactivity. It's like, well, what you can do with private randomness, you can do slightly better with public randomness, but interactivity does not help further. So going back to like that, I just gave up the bounds. That would be the message would be significantly weaker if I had no idea what the state. So we can't do better. That's the use of it. And so I don't know how many of you are familiar with like how to prove those lower bounds, but for discrete distribution estimation, there is like one construction that is basically like you will see it again and again and again. I call that the Paninsky construction because William Paninsky in 2008 used it, but I'm pretty sure people used it before. And this, yeah, the hard case is the uniform distribution. So you want something that's a local perturbation around the uniform distribution. You take something as symmetric as it gets, so you're going to perturb it locally by like multiplicating 1 plus epsilon factor. Why? It's just so that the total radiation distance from the reference uniform is epsilon. So for that, you actually need to put the 2 there. And why do I pair the elements by 2? I'm going to pair the elements by 2, and for each pair, I send it up, down, or down, up. That seems kind of weird, but it's just because it's a parity distribution. I wanted to zoom to 1 without having too much issues, so that's why by doing that pairing, up, down, or down, up, it still seems to the right. But yeah, it's literally like I take the distribution over d elements, I assume d is even, and then I perturb locally by 1 plus or minus epsilon factor, and that should be the hardest given net. You can also think of that as being like now the d over 2 independent derivations to define my construction. I need to figure out the constant fraction of them. That should be hard. And For testing, we use the fact that any such distribution is at distance epsilon from the input distribution, so I should be able to distinguish it from the input distribution. And for learning, what I'm using is any of those two distributions, their distance, like their pairwise distance, is proportional to the number of those d/2 bits that differ. And so, if I want to learn, I have to figure out the constant fraction of those tests. But I've got those information constraints, so now I'm going to put more effort on this. In the centralized setting, putting those variables is half a page. It's going to be more learning. But I can look at the induced distribution of the messages when I get something from one of those distributions. So I draw a sample at random, and then I look at the distribution that induces other messages. This is kind of annoying because for interactive protocols, this is no longer a product distribution. Right? Those things are not IID. And the fact that the message the second person sends can depend on the message the first person sends, well, I don't have an IID thing anymore. So that's going to be like the main issue with those variables is how do we handle that? We don't have that problem for private coin and public coin because then things are like still nice. But I'm not going to give too many details, but there is in our paper we have a general recipe for that, kind of specific for distributed solutions. But first, you lower bound the sum of mutual informations between the total of messages you observe and the bits. You have 0 2 bits. You need to learn them. So you lower bound this thing, the sum of mutual information. Crucially, it's the sum of the mutual information for each bit that you need to lower bound, not the mutual information between the whole vector of bits and the messages. So you lower bound the thing for both learning and testing. I mean, you do that in the case of learning, it's like one thing that everybody uses as well as lemma, so that use basically that version. For testing, there's one tool that I want to use, so look and bound. And then you have a lower bound, so let's get an upper bound. So you get an upper bound on this. This is the harder part. And then as a function of all the parameters you have, and epsilon, d, and that have their channels. And then once you have those two things, you put them together, like you message it, and you hope that the lower bound you get is good. And well, the lower bound you will get depends on like that matrix of this. You can see it as like something more general than that, but in the case of the discrete solution, the particular kind of hard instance layer, this is what it looks like. So it's a PSD matrix. It has a lot of nice properties. In particular, if you message it the right way, the ones you get will depend on the norms, the various norms of that matrix. So there's going to be the continuous norm, the operator norm, and the trace norm. What you get is that. So that looks kind of horrible. This to me, at least, that looks kind of horrible. For learning interactive protocols, basically, you get a d over epsilon squared times d over the maximum possible norm for just this. It is what it is. On testing, you get that thing, but it's also like some weird geometric average of those norms. The cool thing is actually for communication and privacy constraints, bounding those quantities is literally a two-line thing. So that is nice. But that's how interactive. What do we get from the public coin and private coin? Well, you get pretty much the same kind of things, same quantities, same. What you get is these things, and again, if you look at the particular cases of communication and privacy constraints and a few others, you would get the type of bond based on that. Now, you could apply that to many other families of constraints. You can also do heterogeneous constraints. So like some people have privacy constraints, some people can send 5 bits, some people can send like 30 bits, etc. It's just, I mean, the expression, you will get some expression just becomes kind of weird. And one thing I want to say is they make sense. I mean, it's not going to be a surprise to you, but like the norms are related in such a way that like there is no inconsistency between the lower bounds you get. You don't get a lower bound that's like higher for something that should be easier or things like this. So that's good. One thing that I wanted to mention is I said that for privacy and communication constraints, you look at those and you get exactly the right thing, and that's nice. But presumably, you could get a different bound based on this one for interactive and those ones for testing. They don't need to be the same thing. They just happen to be the same thing for both local privacy and communication. We have some examples where they're actually different. So interactivity in some cases help. I don't, but the example we have is not necessarily the most natural constraints. So if someone has in mind like some particular type of natural constraint for which there might be a difference, I'm interested. So like really, the example we have is like kind of weird. That was just finding an example. And yeah, so we are like 3 papers where this one is about public coin and private coin. This one is about interactive protocol. And this one is a generalization just for estimation, not for testing, which allows you to deal with a lot more problems than just discrete distribution estimation and testing. In fact, Gaussian case or other types of problems. So it's a generalization that you only does the estimation part, not the testing. And given the audience, I want to emphasize that like, there are many open questions there, but also there are a lot of connections to strong data processing inequalities and things like this there, which could be interesting. So in particular, a lot of the previous work to prove this was either using Fisher information, which is very much tied to L2 norm, like L2 loss, or strong data processing inequalities on an ad hoc basis. So, oh, you prove something for local privacy, or you prove something for this, or this. And we try to get a more general framework that encompasses those, but there are still some open problems, and like understanding precisely the relation between those techniques would be, I think, very interesting. So that's the first part of the talk. If you have questions about the first part, please go on, because now I'm going to go completely out of my depth. I don't know if I mentioned, but I'm mostly a classical person, so I don't want to say anything too stupid now. But if you have questions for the first part, now is a good time.
You said like W includes identity channel, then the problem becomes trivial, essentially, right?
Yeah.
Do you cover that with the...
Yeah. So yeah, because in the bonds you get in the low bound, basically that becomes vacuous when the identity channel is in it. And in the bonds I gave with like the 2 to the L, etc., implicitly there is like a minimum between 2 to the L.
I mean, the one with the groups.
Yeah. So we will do the fact. In particular, that gives you the most complicated and contrived low bound, like where to prove the low bound in the centralized system.
I've not thought about these things before, but in the public coin setting, can the centralized guy like deduce something from giving the randomness also on the individual like true data, or is it like?
No, all the randomness is independent of the data. The way I think about it is like the public randomness is available to everybody, and then they get the observation. So it's independent of this. Yeah, like there's no. Yeah, that's a good question. Yeah, like the public randomness does not depend on the data. Another thing is that you could extend that in 2 ways. One of them is instead of having private or public, you could have like pairwise randomness. Oh, I have my own private randomness. The other users don't see it, but the server sees it. You can pick up that as like SME along the way. And it's not clear whether there is a separation between this, but that's also, I guess, a natural-ish model. The other one would be, instead of fully interactive, you have like a graph structure and people can actually only communicate in some ways, but that seems to be kind of hard to analyze, except maybe for like some particular structures of that. And the last one is, I assume shared randomness is free, right? If there's public randomness, it's unbounded. If we actually, in another paper, we showed a trade-off between the amount of shared randomness you have, or public randomness, and so we could have a much worse expression than this, where the number of publicly available bits appears on top of the communication, and there's like 2 trade-off between the So I hope I didn't put everybody to sleep at this point. So here what I want to say is like I've been talking about classical things, I want to test the distribution of the T elements in total variation distance. And now I want to learn on test, but I could also, there's a direct analog for quantum setting. So I've got n copies of that d-dimensional mixed state. I want to learn it to trace distance, which, as far as I understand, the trace distance is basically L1 distance between the vectors of eigenvalues. So there's a pretty direct correspondence there. And I can also test. I can also test whether something is the maximum mixed state or far from it in trace distance. I'm using trace distance because now I want to link that to the principles. And again, instead of the maximum mixed state, I could do like any fixed state at any time. So those are natural generalizations of the first theorems. The first question I have for you at this point is, I said that like, in the classical setting, I can just consider the uniform distribution of the testing case. There's a relation between the two. If I can solve the general problem, I can certainly solve the uniform problem. But if I can solve the uniform problem, there's a relation that allows me to like, do some mapping between the two, and I can use a uniformity testing algorithm to solve the more general problem. I don't know if that's the case in the quantum setting. I have no idea, but either way, I think that would be nice to know. But that's the first question. Now, in terms of results, well, those are natural generalizations. Unfortunately, I'm not the one that consider them, but there's a long line of work. I think these are just the last ones I know. But we know to solve it. So for the learning, tomography, d square over epsilon square, I think there was a lot factor in the shape of unnecessary and insufficient copies. So that's 1 on n, the number of copies. And for testing, for both the uniform maximum mixed state or like the more general case, d over epsilon square are necessary. The more general point that you have access to 2 different states and you know neither of them. You want to check the equal. So that's known, as far as I can tell, the problem is fully solved. And you have the same kind of d square square root of d square kind of. For IID test. Yeah. But that requires full entanglement. My understanding of those papers, which I haven't read, and I don't have the mathematical background to read, is you need like the full power of like a joint measurement of all the states to be able to measure those. Which is kind of a problem because, as far as I understand, that's a pretty big ask. So there's been some people asking, what can we do that with simpler measurements? Let's say we don't have entanglement. Even worse, we don't have even adaptivity. So, it's not even sequentially interactive. I make all the measurements at once in a batch. And that fits nicely into the recipe measurement view because then, you have a restricted type of measurements you can make on your copies. And, well, there's a free app now. So it works, of course, but Tuebingen and Lee in 21 proved that the polynomial bonds for the case like in non-adaptive, non-integral case, you need like d to the 3 copies. And they also showed that like adaptively, you can't do as, even adaptively, entanglement is necessary to achieve the linear d thing because the polynomial bond d to the 1.33, and they didn't know whether it was type or not. And then an incomparable group of authors has shown that it's actually tightened with adaptivity. So at this point, what they showed is if you don't have entanglement, you still there's a cost to pay, and adaptivity doesn't help. And that cost is, well, you can look at that and find that like weirdly similar to one of the bonds I showed before. I don't know if I don't know actually if there's something deeper than that or not, but the experiment is the same. And I looked at the proofs of those things, and the techniques are kind of the same, like the proof technique, you still see like Paninsky's construction, like, it's on the diagonal of the matrix. There are no instance, it's like literally you omit that Paninsky construction, and then like, you multiply that by a uniformly rounded matrix, and that gives you the state. You analyze that using the same techniques, but now like proving the concentration you need is, well, worse, like more complicated, but like this is intuitively kind of the same proof. So I'll let you know if there's something deeper than that, or just like, well, once you have a hammer, you'll use it for everything, you know.
So does adaptability means that you can then just store the result of your previous measurements classically?
Yeah. You just decide what to do based on what you have before. So that's my first question. Is there something deeper there, or is it just like, well, syntactically just so happens they look similar, and also like, the techniques are the same just because we only have some techniques and they have to work. And the other ones also are kind of similar too. But another thing I would be really interested in knowing is, okay, so now we understand the case like you have full entanglement, you need to pay D, and you have no entanglement, it's D to the 1.5. Is there like a natural way to go from one to the other? Or like, is it just a sharp threshold? I don't know exactly the frame of the question itself, but that seems like something that might be interesting to understand. Another thing is that they don't consider the difference between public coin and private coin. The lower bound applies to public coin, the upper bound requires shared randomness or this result. But I mean, given everything I've been talking about before, I'd be very interested in knowing that if you just have private randomness, it's actually much worse. And just to give you an idea of what they're doing, to prove the upper bound, it's actually very sadly simple. You take the state, you have n copies of your state, you pick a uniformly random R random matrix, and that gives you a new basis, and you just measure the things in that basis. And you can show that with high probability, with constant probability, it would suffice. Well, if it was the maximum state that you mentioned. But if that was far from it, then your measurement will come. Now it's like you have two possible outcomes. That gives you a probability distribution on D elements, and you can apply the classical algorithm, and that works. Because with constant probability of the choice of the uniformly random matrix, that distribution will be far from uniform. But those require shared randomness among your n measurement. Because if you pick a different random matrix for each of them, then you don't get anything at all. So I don't know if there's something deeper than that, or like there is also a different private coin protocol that just give you also D23R format. I don't know if there are similar separations of homography. I don't think that has been considered. Non-monetary gold homography, and also can ask the same trade-off question. And as I mentioned, I'm really interested in knowing the techniques and frameworks developed in the classical case, if they apply there as well. I mean, it would be nice if we didn't have two different communities looking at analogous problems and just coming up with like similar bounds with similar techniques, but actually there is no underlying unifying principle. I would find that very unsatisfying. So I think that's pretty much all. Thank you, and if you have any questions, I'd be happy to take them.
I may have another one. So, if you look at whether entanglement can help in some of these protocols, I'm asking because if they use these random unitaries, if you add entanglement too much entanglement, these concentration bounds get harder, right? And too much entanglement interacts with the high probability for random unitaries, and then you might actually have to do really new techniques. So that may be, so entanglement is sort of eroded, and that would help to simplify the problem.
Yeah,
and it gets fully closer.
Yeah, I didn't think about that. As far as I can tell, the upper bound for the fully entangled uses completely different ideas than the ones for the non-entangled fit. So I don't know. Yeah, if there is a view that would allow you to do that.
You said that like this sample complexity is essentially the same no matter if you test like for the uniform probability distribution or another probability distribution. But does this require the other probability distribution to be full rank or something like this, or something like that?
So if you only care as with a bound in terms of the domain size, it doesn't require anything. Right? Just so the reduction is basically if I have an explicit reference distribution in my hands. I have a randomized mapping that maps it to like something like a domain of 10 times bigger, etc. And then that distribution is matched to the uniform distribution of that bigger domain. And it preserves L1 distances. So if you were far, you're still far. But what that doesn't give you is all the benefits you might have from the original distribution. So if I want to test identity, like if it's equal to like something that actually it's on the domain of size D, but it's only supported on 3 elements, well, that's going to be mapped to the uniform distribution on 10D elements. So then like, I don't get a better one than square root D. What you might want to do is like an instance optimal kind of noise that depends on some notion of sparsity or things like this. Any other question?
Let's think again.